Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of materials. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising A-Level Physics? The first step is to learn the key facts. Use revision guides, class workbooks, prep notes and textbooks to learn the key ideas of the course. Secondly, you should then be testing yourself. Use things like Caboodle, Seneca, student knowledge checkers, cue cards to quickly test your own knowledge. Finally, use exam preparation books, homework books, study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So, learn the key facts, test yourself, and practice exam style questions. So what are the key facts to do with materials? Well, when a force is added to the bottom of a vertical metal wire of length L, the wire stretches. A material obeys Hooke's law if the extension of the material is directly proportional to the applied force up to the limit of proportionality. The spring constant, which is sometimes called the force constant, is a property of the material being stretched and measures the stiffness of a material. The larger the spring constant, the stiffer the material. Now, Hooke's law applies to both extensions and compressions. The extension of an object is determined by how much it has increased in length. The compression of an object is determined by how much it has decreased in length. Now, the way a material responds to a given force can be shown on a force extension graph. Every material will have a unique force extension graph depending on how brittle or how ductile it is. Now, a material may obey Hooke's law up until a point on your force extension graph. Now, the area between the loading and unloading curves is known as the hysteresis loop. This area represents the work done in stretching a material. This energy is transferred to thermal energy when the force is removed. Now, polythene is a common polymer or polymeric material. It doesn't obey Hooke's law and experiences plastic deformation when any force is applied to it. This makes it very easy to stretch into new shapes, but difficult to return to its original shape. A metal wire obeys Hooke's law and exhibits elastic deformation until its elastic limit. Up to this point, the loading curve is the same as the unloading curve. Beyond this point, it experiences plastic deformation. The unloading curve has the same gradient as the loading curve, and the plastic deformation causes a permanent extension of the wire. Now, the Young modulus is defined as the measure of the ability of a material to withstand changes in length with an added load. This gives information about the elasticity of a material, how stiff it is. The Young modulus can be calculated from the ratio of stress and strain. It is the same unit as stress, pascals, since strain is unitless. Now, just like a force extension graph, stress and strain are directly proportional to one another for a material exhibiting elastic behavior. Therefore, this tells us that the gradient of a stress-strain graph, when it is linear, is equal to the Young modulus. So let's now have a look at some key questions to do with materials. How can the elastic potential energy stored by the object be calculated from this graph? So pause the video now, then unpause the video when you want to go through your answer. Well, it is the area under the straight line section of the graph. Why can the elastic potential energy not be calculated from the area under the curved region? So pause the video now, then unpause the video when you want to go through your answer. Under the curved region, the object undergoes plastic deformation, and energy is therefore dissipated due to this. How is energy being dissipated under plastic deformation? So pause the video now, then unpause the video when you want to go through your answer. Well, at this point, energy is going into moving the atoms of the material into new permanent positions. What material is this a force extension graph for? So pause the video now, then unpause the video when you want to go through your answer. This is a force extension graph for a metal wire. Is this object plastically deformed, and how can you tell? So pause the video now, then unpause the video when you want to go through your answer. Yes, it is. The line does not go back to the origin, indicating that it has been permanently stretched. Why are the two curves parallel? So pause the video now, then unpause the video when you want to go through your answer. It's because the spring constant of the material, which is the gradient of the line, remains constant during both unloading and loading. What material is this a force extension graph for? So pause the video now, then unpause the video when you want to go through your answer. Well, it is a force extension graph for a rubber band. Is this object plastically deformed? How can you tell? So pause the video now, then unpause the video when you want to go through your answer. No, it is not, because the line does go back to the origin, so it's returned to its same shape as when it starts. Why are the loading and unloading curves different? So pause the video now, then unpause the video when you want to go through your answer. Well, at this point, it's because work is dissipated into thermal energy when a force is being placed onto a material stretching it. What material is this the force extension graph for? So pause the video now, then unpause the video when you want to go through your answer. It is a force extension graph for a plastic object. How can you tell that this material does not obey Hooke's law? Pause the video now, unpause the video when you want to go through your answer. It's because the force extension graph is not a straight line. A force is placed on a material, stretching it. What type of force is this and why? So pause the video now, then unpause the video when you want to go through your answer. It is a tensile force, as the material is being extended. This material has a force and a stress placed on it. What is the difference between the two? So pause the video now, then unpause the video when you want to go through your answers. A tensile force will cause an object to extend. The stress is the force placed on the object per unit area. This material undergoes an extension and a strain. What is the difference between the two? Pause the video now, then unpause the video when you want to go through your answer. An extension is the change in length of an object that it undergoes when a force is placed on it. Strain is the ratio of the extension to this original length. Two objects of different dimensions but the same material have the same force placed on it. Do they have the same or different spring constants and why? So pause the video now, then unpause the video when you want to go through your answer. The two objects will have different spring constants, as the spring constant is dependent on the dimensions of the object. Two objects of different dimensions but the same material have the same force placed on it. Do they have the same or different Young moduli and why? Pause the video now, then unpause the video when you want to go through your answer. The two objects will have different Young moduli, as the Young's modulus is a constant for a material. From looking at this graph, which material is the strongest and why? So pause the video now, then unpause the video when you want to go through your answer. The answer is A, because it needs the greatest force to break it, as it has the highest value of stress in the graph and the highest value of breaking stress on the graph. Which material is the stiffest and why? Pause the video now, then unpause the video when you want to go through your answer. A is the stiffest as it has the steepest gradient. Which material is the most brittle and why? Pause the video now, then unpause the video when you want to go through your answer. B is the most brittle as it breaks with the least plastic deformation. Which material is the most ductile and why? Pause the video now, then unpause the video when you want to go through your answer. C is the most ductile because it extends the most. Which material is the weakest and why? Pause the video now, then unpause the video when you want to go through your answer. D is the weakest as it breaks with the lowest stress. As you can see on the graph, it has the least value of stress of the values given. A cube of copper has a mass of 240 grams. Each side of the cube is 3 centimeters long. Calculate the density of copper in grams per centimeter cubed and in kilograms per meter cubed. Pause the video now, then unpause the video when you want to go through your answer. The volume of the cube is 3 times by 3 times by 3 centimetres, so it's 27 centimetres cubed. Density is mass over volume, so it's 240 over 27, which is 8.89 grams per centimetre cubed. To turn it from that into kilograms per metre cubed, you will multiply by 1,000, so it's 8,890 kilograms per metre cubed. The density of steel is 7,850 kilograms per metre cubed. Calculate the mass of a steel sphere of radius 0.15 metres. Pause the video now, then unpause the video when you want to go through your answer. The volume of a sphere is 4 over 3 pi r cubed. Pop in the values, you get 0.0141 meters cubed. Density is mass over volume, so mass is density times by volume. Work it all through, we get 111 kilograms. Calculate the average density of a neutron star of mass 3 times 10 to the 24 kilograms and a radius of 12 kilometers. Pause the video now, unpause the video when you want to go through your answer. The volume of a star, we're going to assume it's a spherical shape, so it's 4 over 3 pi r cubed. Pop in our values, and then we also know that density is mass over volume. Remember, we convert kilometers into meters, and we get our answer to be 4.1 times 10 to the 11 kilograms per meter cubed. An 18-carat gold bar of volume 3.34 times 10 to the minus 6 meters cubed comprises of 58.2% gold and 41.8% copper by volume. Calculate the density of the bar. State any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. The mass of the gold is going to be density times by the volume, so it's going to be 0.582, the percentage of the volume that is gold, times by 3.34 times 10 to the minus 6, times by 1.93 times 10 to the 4, 3.75 times 10 to the minus 2 kilograms. The mass of copper, again by the same logic, is 0.418 times by 3.34 times 10 to the minus 6, times by 8.96 times 10 to the 3, is 1.25 times 10 to the minus 2 kilograms. Density is the total mass, so the two values added, over the total volume given in the question, so therefore our answer is going to be 1.50 times 10 to the 4 kilograms per meter cubed. And this assumes that the copper and the gold do not react with each other, and the atoms don't change separation length when they're mixed together. The following figure shows the force extension graphs for 4 springs, A, B, C and D. State which spring has the greatest value of spring constant. So pause the video now, then unpause the video when you want to go through your answer. The answer is spring D, as the graph has the steepest gradient. State which spring is the least stiff. Pause the video now, then unpause the video when you want to go through your answer. The answer is spring A, as it extends the most for each unit of force applied. State which of the 4 springs does not obey Hooke's law. Pause the video now, then unpause the video when you want to go through your answer. Spring C does not obey Hooke's law, as there's no section of the graph that forms a straight line. The following figure shows a force extension graph for 2 materials. State which polymer has the greatest stiffness. So pause the video now, and then unpause the video when you want to go through your answer. The answer is A, because there's the less extension per unit force, or the steeper gradient. State which polymer requires the greater force to break it. Pause the video now, then unpause the video when you want to go through your answer. A requires a greater force to break it, as the line continues to a higher value of force. State which polymer requires the greater amount of work to be done in order to break it. So pause the video now, then unpause the video when you want to go through your answer. B requires the greater amount of work to be done to break it, as there's a larger area under the graph. A force of 12 newtons extends a rubber band by 18 centimeters. Estimate the energy stored in this rubber band. Explain why it can only be an estimate. So pause the video now, then unpause the video when you want to go through your answer. Right, the elastic potential energy is equal to a half Fx, so it's a half times by 12 times by 0.18, 18 centimeters into meters. That gives us 1.1 joules, and we're assuming the rubber band will obey Hooke's law. A spring has a force constant of 4,800 newtons per meter. Calculate the elastic potential energy when it's compressed by 2 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Well, elastic potential energy is a half Fx or a half kx squared. So it's a half times by 4,800 times by 0.0020 squared, which is millimeters into meters. So we get 9.6 times 10 to the minus 3 joules. For each of the materials whose stress strain graph is shown in the figure, deduce the values of the Young modulus and the breaking stress. So pause the video now, then unpause the video when you want to go through your answer. So for material A, the Young modulus is stress over strain. So you look at the values on the graph and you go to 150 times 10 to the 6, remember it's megapascals on the side, divided by 0.003, remember we turn percentages into values, so we divide by 100, so you get 50 gigapascals, and the breaking stress is the maximum value, which is 150 megapascals. Material B, the Young modulus is 100 times 10 to the 6 over 0.001, which is 100 gigapascals. Now this can only be found for the straight line portion of the stress strain graph. The breaking stress is the maximum value, the peak, so it's 130 megapascals. Next one, material C, we know that the Young modulus is stress over strain, so it's 100 times 10 to the 6 over 0.004, which is 25 gigapascals, and the breaking stress is the maximum possible value, 100 megapascals. Let's now have a look at some exam style questions. A manufacturer is testing a new type of dynamic climbing rope designed to stretch under sudden loads to reduce injury risk. A 1.50 meter length of rope with a cross-sectional area of 8 times 10 to the minus 6 meters squared is tested by applying a steadily increasing tensile force. At one point during the test, the force applied reaches 360 newtons and the rope extends by 9 millimeters. The rope remains within its elastic limit during this test. Calculate the Young modulus of the rope material using the data provided. Discuss how the rope's design balances safety and performance. Include an explanation of why a high and low Young modulus could be problematic in climbing ropes. And in the second test, the rope is loaded rapidly in a simulated fall, and the force rises to 950 newtons. Evaluate what additional information will be needed to determine whether the rope is likely to snap. Suggest one method of improving the rope's resistance without significantly increasing its stiffness. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we know that the extension is 9 times 10 to the minus 3 meters. The Young modulus is force times by length over area times by extension. Pop in all the values, work it through, and we get 7.5 times 10 to the 9 pascals. Now a high Young modulus will lead to a stiff rope with little stretch. Now this will reduce the fall distance but increase the impact force, leading to a greater injury. A low modulus would lead to a soft rope with a safer fall but excessive stress, which may cause the climber to hit the wall of the ground. So the ideal rope should have a controlled stretch, so be elastic enough to absorb energy but strong enough to hold the load. Now you will need to know the ultimate tensile strength or the stress strain graph is needed to compare against a 950 newton stress. We need to have knowledge of the rope's elastic limit and the breaking stress. So an improvement would be to use braided fibers or woven cores, as this will increase the strength without changing the stiffness. So the design spreads the load across the fibers, improving the toughness without raising the Young modulus. An instrument technician is testing various steel guitar strings of different thicknesses and lengths. Each string must vibrate freely without plastic deforming when under high tension. The Young modulus of the steel is known to be approximately 2 times 10 to the 11 pascals. In one experiment, a string length of 0.65 meters and a diameter of 0.90 millimeters is tensioned with the force of 200 newtons. Conclude if the string will snap. The typical breaking stress of steel is 4 times 10 to the 8 pascals. Another string of the same material is stretched and found to extend by 1.2 millimeters when tensioned. Given that its original length is 0.80 meters and its diameter is 1.20 millimeters, determine the tensile force applied. Then the technician is considering replacing steel with a polymer material that has a much lower Young modulus. Evaluate the implications of this change for the playability and the acoustic performance of the guitar. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the area is pi r squared because you assume it's a circle. So we work it through, remember diameter is halved and turned into meters, so therefore we get 6.36 times 10 to the minus 7 meters squared. Stress is force over area, so we get 3.14 times 10 to the 8 pascals, so the string is approaching but is still below the breaking stress. Next one, we know that 1.2 millimeters will turn to 1.2 times 10 to the minus 3 meters. Strain is the extension over the length, so therefore it's 1.5 times 10 to the minus 3. Stress is the Young modulus times by strain, so pop in all the values, it's the same material, so it's the same Young modulus, so it's 3 times 10 to the 8 pascals. The area, because we assume it's a circle, is pi r squared. Remember that we're going to be using the radius again in meters, so therefore we get 1.13 times 10 to the minus 6 meters squared. So force is stress times by area, so we get 339 newtons. A lower Young modulus will lead to a greater extension with the same tension, so the string may feel loose or slack to the musician. So this would mean that our vibration frequency would decrease, so therefore the pitch produced could be too low. Now a softer material could dampen the sound, reducing the volume and the clarity of the sound wave. A student is investigating how different materials respond to stretching. They test two wires, wire A and wire B of equal length 1.20 meters and diameter 1 millimeter. Both wires are stretched with the same force of 35 newtons. A wire A extends by 2.8 millimeters and wire B extends by 1.7 millimeters. The density of wire A is 8 times 10 to the 3 kilograms per meter cubed, and the density of wire B is 2.7 times 10 to the 3 kilograms per meter cubed. Determine by calculation which wire is stiffer. Given that both wires have identical volume, determine the ratio of their masses. Then the student claims that wire B is better for lightweight structural applications because it is stiffer and lighter. Evaluate the statement using your previous answers. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the area is pi r squared. Remember, we will take the diameter and half it to get the radius and turn it into meters. So the area is 7.85 times 10 to the minus 7 meters squared. The Young modulus of each one is force times by length over area times by the extension. So for A, that gives us 1.91 times 10 to 10 pascals, and for B, it gives us 3.14 times 10 to 10 pascals. So therefore, wire B is stiffer as there's a higher Young modulus. Now the volume is the same for both, so we know volume is the area times by the length, so it's 9.42 times 10 to the minus 7 meters cubed. The mass of A is therefore the density times by the volume, so we get 7.54 times 10 to the minus 3 kilograms for A, and then for B, 2.54 times 10 to the minus 3 kilograms for that one. So our ratio is the two numbers divided by each other, which is 2.97. Now wire B is stiffer, so it'll be better at resisting extension. And wire B is lighter, which is confirmed by the mass comparison. But it may be more brittle or have a lower ultimate tensile strength, which we don't know. So the claim made is reasonable, but more data is needed to fully justify its use for structural uses. Scientists are designing footwear for astronauts exploring Mars. To absorb impact, the soles are made of a synthetic springy slime that behaves elastically up to a certain limit. A prototype sole is compressed vertically, and the restoring force is measured for different compressions, with the following results obtained. Use the data to determine whether the springy slime obeys Hooke's law across the range tested. Estimate the spring constant of the slime when Hooke's law is valid. Explain how this would influence the astronaut's experience when walking on Mars. Then evaluate whether this material is suitable for long-term use in the sole of the boot based on the data provided. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we've got to calculate the ratio of F to X for each value. So for each one, we get 720 newtons per meter, 740 newtons per meter, 730 newtons per meter, 735 newtons per meter, and 700 newtons per meter. And then the last value, we get 597 newtons per meter. So the first 5 points are roughly consistent, so you get in a linear pattern, so they will be obeying Hooke's law. But the final value deviates significantly, indicating you got a non-linear region. So the conclusion is that Hooke's law is obeyed up to 0.050 meters. Now, using the data within the linear range, we can see that the spring constant is about 735 newtons per meter. That's soft enough to absorb the impact, but stiff enough to support the body. Now, on Mars, the gravity is about 38% that of the Earth's, so this will need a reduced force, but the spring will still provide a firm rebound, so it's suitable for this climate on Mars. Now, we know that there's deviation from the Hooke's law at higher compressions. Now, the material may deform or behave unpredictably during these larger loads, so long-term wear may lead to plastic deformation or fatigue. So it might be suitable for walking, but not for running or jumping, and we need more testing to see if that was valid. A prototype spring-loaded catapult is being developed to launch a rescue capsule away from a damaged aircraft. The capsule is launched horizontally from rest using two identical large springs. Each spring has a spring constant of 5,900 newtons per meter and is compressed by 0.75 meters before launch. The combined mass of the capsule and occupant is 65 kilograms. The friction and air resistance are negligible during the initial launch. Before launch, each spring in the catapult system is compressed by 0.75 meters. Determine how much energy this compression stores in the system and explain what this implies about the total amount of mechanical energy initially available for the launch. The capsule and occupant are launched horizontally from rest using the compressed springs. Assuming that the stored energy is fully transferred to the motion of the capsule, calculate its launch speed. Use your result to assess whether this method of launch appears adequate for achieving high-speed emergency ejection. In later tests, the capsule consistently fails to reach the required minimum speed of 15 meters per second. Evaluate the possible causes for this shortfall based on energy principles and suggest two changes to improve performance. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know E equals a half kx squared. Pop in all the values, you get 421.875 joules. Now the total energy is from two springs, so therefore in total the energy is 843.75 joules. So this is the total mechanical energy available for launch, assuming there's no losses in energy. Now we know that the elastic energy will turn into kinetic energy, which equals a half mv squared. So we pop that into the equation and V equals 5.09 meters per second. Now this speed is relatively low for the rapid emergency ejection system, so the launch mechanism does not appear to be adequate to meet the expected performance needed for a high-speed escape, suggesting underperformance. Now the actual speed is below the target 15 meters per second. Now this could be because not all energy is transferred. Ideally it will be lost to friction, sound and heat. There's compression on the spring, and also we could use springs with a high spring constant so it's stiffer, or we could reduce the mass of the capsule. Now the higher spring constant or lower mass would lead to a greater acceleration from the same resultant force, leading to a higher speed for the capsule. A solid spherical component has a diameter of 0.06 meters and a mass of 0.35 kilograms. The component is made from an unknown material. Calculate the volume of the spherical component. Calculate the density of the unknown material. So pause the video now, then unpause the video when you want to go through your answer. Well, the radius is going to be 0.03 meters. V equals 4 over 3 pi r cubed. So we pop in the values to be 113.1 times 10 to the minus 6 meters cubed. Density is mass over volume, so it's 0.35 over that value, which is 3,094 kilograms per meter cubed. Our next question says, a student carried out the investigation on the spring to test this following information. She applied a range of forces from 0 newtons to 5 newtons to the spring. She measured the length of the spring and recorded the extension for each force, and she plotted the graph of force against extension. Determined the stiffness of the spring, then discussed the extent to which the student's results are consistent with the information given by the manufacturer. So pause the video now, then unpause the video when you want to go through your answer. Right, the stiffness of the spring is the gradient of the graph. So you draw a straight line through the data. We can then work out the gradient by doing 5 over 0.25, and it's 20 newtons per meter. So we know that the spring constant is roughly going to be 21 plus or minus 1.055%. So it's between 19.95 and 22.04. We know that the force is going to therefore be 8 newtons applied to it, and our elastic potential energy is going to be 12 times by the force times by the extension. So it's 8 times by 0.4, 1.6 joules. So we do get a straight line graph through the origin, which is consistent with Hooke's law. They also indicate that the maximum extended length is not covered by the student's results in the information given. The calculated value is compared with the data needed of 1.6 joules. We conclude on this. We use our percentage uncertainty to determine the range in K, which we've just done, and calculate the percentage difference between K and the value of 21 and see if that leads to a difference of more or less than 5%. A type of exercise device is used to provide resistive forces when a person applies compressive forces to its handles. The stiff spring inside the device compresses as shown in the figure below. The force exerted by the spring over a range of compressions was measured. The results are plotted on the grid below. State Hooke's law, then state which two values of the graph confirm that the spring obeys Hooke's law over the range of values tested, and use the graph to calculate the spring constant stating an appropriate unit. So pause the video now, then unpause the video and you'll want to go through your answer. Right, in our first one, we know that the deformant force on a material is directly proportional to the extension of the material it causes up to the elastic limit. We know it has a line of best fit, which is a straight line and through the origin. Now again, we work out the gradient of the line and we should get it to be 1290 newtons per meter. A manufacturer of springs tests the properties of a spring by measuring the load applied each time the extension is increased. The graph of load against extension is shown below. State Hooke's law, calculate the spring constant and state an appropriate unit. Use the graph to find out the work done in extending the spring up to point B. Beyond point A, the spring undergoes plastic deformation. Explain the meaning of the term plastic deformation. So pause the video now, then unpause the video and you want to go through your answer. Hooke's law is where the force is proportional to the extension up to the limit of proportionality. The spring constant will be the gradient of the line of the straight line section of the graph. So we get about 1100 newtons per meter. The area under the straight line section of the graph, which it will give you the elastic potential energy or the work done in extending the spring. So you can work it through and you get the answer to be 1.1 joules. Now plastic deformation is the permanent extension when the deformant force is removed. A spring has a spring constant of 240 newtons per meter with a tolerance of 5% supplied by the manufacturer. The maximum energy that the spring can store safely is 90 joules. A lab technician uses the spring in an experimental arrangement and measures the extension with a ruler that has a resolution of 1 centimeter. The extension is recorded as 85 centimeters. Determine the energy stored in the spring along with its absolute uncertainty and explain why it might not be safe. So pause the video now. Then unpause the video and you want to go through your answer. Right, the work done is a half times by kx squared. So from the information given, it's 86.7 joules. Now our percentage uncertainty is going to be 0.05 plus 2 times by 1 over 85, which is 0.07. So therefore our absolute uncertainty is going to be 0.07 times by 86.7, which is 6 joules. Now that is higher than 90 joules, which is the safe value, because 87 plus 6 would be 93. So therefore this is actually unsafe. A student investigated how the extension of the rubber cord varied with the force used to extend it. She measured the extension for successive increases of the force and then for successive decreases. The diagram below shows the graph of her results. Give a reason why the graph shows the rubber cord does not obey Hooke's law. Give a reason why the graph shows the rubber cord does not exhibit elastic behavior. What physical quantity is represented by the area shaded on the graph between the loading curve and the extension axis? Then describe the procedure and measurements you would make to carry out this investigation. So pause the video now, then unpause the video and you want to go through your answer. Right, in this first one, we know it doesn't obey Hooke's law because the lines are not straight. It doesn't exhibit plastic behavior because there's no permanent extension. It returns back to its origin position. The physical quantity, which is under the line, is the work done or the energy stored on the rubber cord. So you would draw a diagram showing the rubber cord fixed at one end supporting a weight at the other end or being pulled by a force. You'd describe how you can apply a variable force, so either putting different masses on or have a Newton meter. You would measure the cord with the rulers or draw that procedure, measure the force applied or have your known weights, measure your extension of your cord, repeat this for then increasing and decreasing lengths, and you can work out your extension from the cord length minus the initial length of the cord. A stress-strain graph for a ductile material is shown. Identify and describe the key features shown by the graph. Reference to atoms, ions or molecules is not required. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, that we know the ductile material obeys Hooke's law and undergoes the elastic stretching both when as shown by the linear portion. Now, the limit of the linear portion is called the limit of proportionality, and the gradient of the linear portion is the Young modulus of the material. Just beyond our limit of proportionality is our elastic limit. Beyond this point, the material does not return to its original shape. The yield point is the point at which the material undergoes a large increase in strain for little or no increase in stress. The maximum stress is called the breaking stress, or the ultimate tensile stress. The material will continue in the plastic stage until the breaking point. Now the curve bends downwards beyond the maximum stress because this sample is necking. It is exhibiting a great a region of where it is extending without much actual stress being applied or change of stress being applied to it. A steel object is held by an electromagnet. The magnetic force prevents the steel object falling. State 2 reasons why the weight of the object and the force of the electromagnet are not a Newton's third law pair. The electromagnet is suspended from a support by a steel cable. When the object is suspended, the strain in the cable is 3 times 10 to the minus 4. Calculate the Young modulus of the steel in the cable. Then the force extension graph for the steel cable is shown below. When the electromagnet is switched off, the steel object falls. A student states that the change in the elastic strain energy stored in the cable will be transferred to the gravitational potential energy of the electromagnet. Discuss the student statement, and you should add it to the force extension graph as part of your discussion. So pause the video now, then unpause the video when you want to go through your answer. Right, they are not going to be a Newton's third law pair, as they act on the same object and they are not the same type of force. We know that the extension is going to be equal to the Young modulus times by the length. So we work that through, we get 1.14 times 10 to the minus 3 meters. We know from Hooke's law, force is equal to spring constant times by extension. So with all the values given, we can work out force to be 3.19 times 10 to the 4 newtons. We know stress is force over area. Again, we can work it all through to be 6.26 times 10 to the 7 pascals. So our Young modulus is the stress over the strain, so we get to 2.09 times 10 to the 11 pascals. Now the area under the graph will be the elastic strain energy. Now the weight of the electromagnet is still going to be exerted on the cable after the object falls. So the change in the elastic strain energy will be equal to the area under the graph between the total weight and then the weight of the electromagnet. So any change in the gravitational potential energy of the electromagnet will be the weight of the electromagnet times by the change in the extension. So therefore, the change in the elastic strain energy stored will always be greater than the change in the gravitational potential energy of the electromagnet. So that brings an end to our revision session today. If we've been successful and we've learnt in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this revision session on materials, which is part of the Paper 1 exam for AQA A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of materials. So in today's revision session we're going to look at how you can answer examination questions for AQA A-Level Physics Paper 1 on the topic of materials. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics and understand what topics you need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you're writing full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's have a look at how you should be revising A-Level Physics. So the first thing you should be doing to independently revise for A-Level Physics is to learn the key facts. Use the revision guides, class workbooks, the student prep notes and textbooks to learn the key ideas of the course. You might wish to do this by making mind maps or writing out notes yourself. The second step is to test yourself. So use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, we should be practicing examination style questions. questions. So use examination preparation books, homework books, supervised study books and additional workbooks to answer examination questions and mark your own work. Now you may wish to download your own examination past papers to do this. So the 3 steps would be to learn the key facts, then to test yourself, and then to practice examination style questions. Now in this revision session we'll be looking at the 3 different types of questions. We'll be looking at general check questions, which are basic questions designed to probe your understanding of the key concepts of the topic. Then we'll look at checkpoint questions, which are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. And then finally we'll have assessment point questions, which are past paper examination questions which will mimic the type of questions found in upcoming public examinations. So let's now have a look at the topic of materials. So in our first question, a cube of copper has a mass of 240 grams. Each side of copper is 3 centimeters long. Calculate the density of copper in first grams per centimeter cubed and then in kilograms per meter cubed. Then the density of steel is 7,850 kilograms per meter cubed. Calculate the mass of a steel sphere of radius 0.15 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question you've got to remember how you can work out the volume. So you can work out the volume of the cube by multiplying the side by 3 times. So 3 times by 3 times by 3, which is 27 centimeters cubed. We then know the equation is density is mass over volume, so we can put 240 over 27 to get 8.89 grams per centimeter cubed. You would then multiply that by 1,000 to get, divide that by 1,000 to get that into kilograms, but then also you'd multiply by 10 to the 6 because you go from 10 to the minus 2 to back to 10 to the 0, but you've got to do it 3 times, so therefore it's 10 to the 6. Okay, and it's because it works through because it's divided by meters cubed, so therefore it's 8,890. The next question, you're going to have to work out the volume of the steel sphere. So you can say the volume is 4 over 3 pi r cubed, pop in all the values, then say density is mass over volume, so mass is density times volume, work it out and get 111 kilograms. The next question says, a measuring cylinder is filled up with water to its 70 centimeter cube mark. An irregular mass of 0.08 kilograms is gently placed into the water. The new water level mark is 85 centimeters cubed. Calculate the density of this new rock. The next question says, calculate the average density of a neutron star of mass 3.0 times 10 to the 24 kilograms in radius 12 kilometers. Then an 18 karat gold bar of volume 3.34 times 10 to the minus 6 meters cubed comprised of 58.2% gold and 41.8% copper by volume. Calculate the density of the bar and state any assumptions made. The density of gold is 1.93 times 10 to the 4 kilograms per meter cubed, and the density of copper is 8.96 times 10 to the 3 kilograms per meter cubed. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question we need to say that density is mass over volume. Now you know what the mass is from the question, is given to you, but the volume is the difference in water level from when you have the object out of the water to when it's fully submerged in the water, because the object will displace the same volume of itself, okay, in that liquid it's immersed in. So you can work it through, and remember we want to go from centimeters cubed to meters cubed. That's done by multiplying by 10 to the minus 6 because it's 10 to the minus 2 3 times, so that's 10 to the minus 6, so we get 5.3 times 10 to the 3 kilograms per meter cubed. Now in our next question we can again say what's the volume. Well, it's a star, so we assume it's a sphere, so we say it's 4 over 3 pi r cubed. We convert 12 kilometers into meters by saying it's 12 times 10 to the 3. We can then say density is mass over volume and pop in all the values there, and then we get 4.1 times 10 to the 11 kilograms per meter cubed. In this next question, when you've got an alloy, what you would do is you'd work out the mass of each individual metal. So you'd say, well, you've got 58.2% gold, so it's 0.582, times by the density of gold, times by the volume that it will have, which would be 3.34 times 10 to the minus 6. So you get the mass of gold out. You do the same for copper, but again it's 41.8%, so it's 0.418. Then you got your 2 masses. You then will add the 2 masses because the mass will have to be conserved in total when you have them as an alloy. Okay, and then you divide it by the volume of the alloy, which you know about before, so we get 1.50 times 10 to the 4 kilograms per meter cubed. Now remember, this calculation assumes that the copper and gold don't react with each other and the atoms don't change separation length when mixed and have that consistent density. The next question says, figure 7.8 shows the force extension graphs of 4 springs, A, B, C and D. State which spring has the greatest value of spring constant, state which is the least stiff, and state which of the 4 springs does not obey Ohm's law. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we know that on the force extension graph, the spring constant is the gradient. So spring D has the greatest value as it has the steepest gradient. Now stiffness is another measure of saying spring constant. So spring A is the least stiff because it has the least gradient, or it extends the most for each unit of force applied. And then the next one, which doesn't obey Hooke's law, well, we know in a force extension graph, an object that obeys Hooke's law must have a straight line section to it. Spring C at no point has a straight line section, so it does not obey Hooke's law at any point. The next question says, a force of 12 newtons extends the length of rubber band by 18 centimeters. Estimate the energy stored in this rubber band. Explain why your answer can only be an estimate. And then a spring has a force constant of 4,800 newtons per meter. Calculate the elastic potential energy when it's compressed by 2 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that we need to work out the elastic potential energy because we know that it's an elastic object that's being extended. So we can say the elastic potential energy is equal to a half Fx, that's an equation given to you, pop in all the numbers and we get 1.1 joules, but this can only be an estimate because we're assuming that the rubber band is obeying Hooke's law and is acting like an elastic object, which is only an estimate. In this next one, now we're not given the force, but we are given the spring or force constant, so we can use the other equation for elastic potential energy. So we say it equals a half kx squared because we know that F equals kx. So therefore it's a half times by 4,800 times by 2 times 10 to the minus 3 because millimeters into meters all squared, which is 9.6 times 10 to the minus 3 joules. The next question says, figure 7.17 shows force extension graphs of 2 materials. For each of the following questions, explain how to deduce your answer from the graphs. State which polymer has the greatest stiffness. State which polymer requires the greater force to break it, and state which polymer requires the greater amount of work to be done in order to break it. So pause the video now, then unpause the video if you want to go through your answer. Right, we know that in a force extension graph that stiffness is again the gradient of the graph, so therefore A has the greatest stiffness because it has the steeper gradient. The one that needs a greater force to break it is the one which has the highest ultimate tensile strength, which is the biggest value on the graph. So therefore A, because it'll have a greater value of force on the graph, you can see from the line it's a higher point on the y-axis. And then finally, the amount of work to be done, or the toughness, is the area under the graph, which is B, because you can see it has a larger area there. The next question says, sketch a force extension graph for a spring which has a spring constant of 20 newtons per meter and which obeys Hooke's law for forces up to 5 newtons. Your graph should cover forces between 0 to 6 newtons and show values on both axes. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, you need to have a y-axis, which is labelled with force, with the units of newtons, and the x-axis with extension with the units of meters. You should have a straight line graph from the origin to where the force is 5 newtons, because it's obeying Hooke's law, so it'll be a straight line, and you get the extension to be 0.25 meters at that force of 5 newtons, because we've said force equals spring constant times by extension, so extension is the force over the spring constant, so you'll see that it works out to 0.25. After the straight line, it will still increase so after the straight line section the line will still increase, but it will start to curve, so therefore the gradient will decrease. The next question says, rubber is an elastic material. Explain what this means. Then explain why a rubber band does not have a spring constant. Then compare and contrast the behaviour of a metal wire and a strip of polythene. Then the figure below shows the force extension graph for a length of bungee cord. Use the graph to estimate the thermal energy released when the cord is stretched by 0.4 meters and returned to its original length. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to know what the definition of elastic is. Elastic is when an object will return to its original length when the extending forces acting upon it are removed. Now, rubber will not have a spring constant because the force extension graph for rubber will not have a straight line through the origin section. It won't obey Hooke's law, so therefore it can't have a spring constant because there's no straight line section. That's the only time you can get a spring constant. The next one, we've got to be aware that a metal wire has elastic behavior up to its elastic limit, and then beyond that it will actually show inelastic deformation. It'll still extend but not in that linear pattern. Now polythene won't show any elastic behavior at all. It'll only show inelastic deformation throughout its entire stretching journey. Now the next one, how can you work out the thermal energy release? Well, the thermal energy release is the difference between the areas from the loading graph to the unloading graph. So it's the area of that hysteresis loop, which we call the process by which energy is lost by thermal energy in this method is called hysteresis. So here you can count approximately that between the two lines there are 4 squares. Now each square is worth 1 joule because it's 0.1 on the x-axis times by 10 on the y-axis, so it's 1 joule. So it's 4 times by 1, which is 4 joules. The next question says, a rubber band is extended by 20 centimeters by a force of 18 newtons. Estimate the energy stored in the rubber band. Then the energy stored in a stretch cable is 1.5 joules when it's extended by 2 millimeters. Calculate the spring constant of the wire. Then below is a force extension graph for spring. Calculate the work done on the spring when the extension changes from 5 centimeters to 15 centimeters. Then a spring of mass 8.0 grams has a spring constant of 120 newtons per meter. It is placed upright on a horizontal table and compressed by 4 centimeters. It is then released and it jumps vertically above the table. Calculate the maximum height gained by the spring above the table. State any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, we know elastic potential energy will be the energy stored in the rubber band as it's an elastic object. So it's a half Fx, pop in all the values, centimeters turned to meters, 1.8 joules. In the next question, we can say that E equals a half kx squared, therefore K equals 2E over x squared. Remember our millimeters turn to meters, so it's 2 times 10 to the minus 3. So it's therefore 7.5 times 10 to the 5 newtons per meter. Now in our force extension graph, it's going to be that the work done is the area under the graph. So therefore it's going to be a half times by 0.1 times by 15 minus 5. So it works through to be 1 joule. Now in this next question, what we're saying is the elastic potential energy, well, we are given the spring constant and we know the compression, so therefore we can say it's a half kx squared. Remember, compression is just extension in the opposite direction, so therefore it's a half times by 120 times by 0.04 squared, so therefore you get 9.6 times 10 to the minus 2 joules. You can then assume all the elastic potential energy will go to gravitational potential energy, so therefore we can then say that this value will equal mgh, so h will equal 9.6 times 10 to the minus 2 over 0.008, which is the grams into kilograms, times by 9.81, which is 1.2 meters. The next question says, list the metals in the table below from the stiffest to the least stiff. Then which of the non-metals in table 1 is the stiffest? So pause the video now, then unpause the video when you want to go through your answer. Well, you should be aware that stiffness is pretty much linked to the Young modulus. So the most stiff objects are the ones with the highest Young modulus, and the least stiff objects are the ones with the lowest Young modulus. So this tells us that the stiffest non-metal in this example previously was glass, because it had the highest Young modulus for an object which was not a metal. The next question says, figure 7.12 shows stress strain graphs for 2 materials, A and B. Use the graph to determine the Young modulus of each material. A piece of steel wire 200.0 centimeters long having a cross-sectional area of 0.50 millimeters squared is stretched by a force of 50 newtons. Its new length is found to be 200.1 centimeters. Calculate the stress, the strain and the Young modulus of steel. Then calculate the extension of a copper wire of length 1.00 meters and diameter 1.00 millimeters when a tensile force of 10 newtons is applied to the end of the wire. The Young modulus of copper is 130 gigapascals. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, you've got to remember that you can work out the Young modulus by doing the gradient of a stress strain graph, but it has to be the straight line section. So you can do it for A by doing stress over strain of the straight line section and getting 1.5 gigapascals, and then the same for the straight line section of the B line, okay, and so therefore you get 5 gigapascals. Now in this next question, we can work out stress because we know stress is force over cross-sectional area, so it's 50 times by by 0.5 times 10 to the minus 6 millimeters squared into meters squared. So therefore it's 1.0 times 10 to the minus 8 pascals. We know strain is extension over the original length. So the extension is going to be 0.1 because it's going from 200.0 to 200.1 centimeters. We divide it by 200.0, the original length, and we get 5 times 10 to the minus 4. We don't need to change the units because it's a ratio, so they will cancel through. The Young modulus is then stress over strain, so we get 2.0 times 10 to the 11 pascals. Now in this next question again, we know that strain is stress over the Young modulus, which we know is x. It's going to be the extension over the original length is equal to the force over the area times by the Young modulus. We know here that the area is going to be pi d squared over 4 because that's just it's just a circle. So therefore the extension is going to be 4fl over pi d squared times by e. Pop in all the numbers. Remember, we go from millimeters into meters and we go from gigapascals into pascals. So therefore we get 9.8 times 10 to the minus 5 meters. Right, so now next question, it says a sample of fishing line is 1.0 meters long and is of cross-sectional circular radius 0.25 millimeters. When a weight is hung on the line, the extension is 50 millimeters and the stress is 2.0 times 10 to the 8 pascals. Calculate the cross-sectional area of the line, the weight added, the strain in the line, and the Young modulus. So pause the video now, then unpause the video and you'll want to go through your answer. Right, so cross-sectional area, it's a circle, so we can say it's pi r squared. So again, remember, we're going to convert our millimeters into meters, so it's 0.25 times 10 to the minus 3. So you pop in all the numbers and you get 2.0 times 10 to the minus 7 meters squared. In this case, the weight is the force, and the weight is the thing that is causing the stress on the object. So therefore, weight is equal to stress times by area, because we know stress is force over area, and the force in this instance is the weight. Pop in all the numbers and we get 39 newtons. Strain is extension over length. Now we know both these values, we've given both this information, but they've got to be in the same unit, so we'll convert our millimeters into meters and we get 0.050. And then finally the Young modulus is stress over strain, so you can pop in those two values and we get 4.0 times 10 to the 9 pascals. The next question says, explain what is meant by the ultimate tensile strength of a material. Describe the properties of the cast iron from the graph shown below. Then a metal has a diameter of 0.20 millimeters. A force of 6.3 newtons changes its length from 1.05 meters to 1.048 meters. Calculate the Young modulus of the material. Then the ultimate tensile strength of a metal is 220 megapascals. Calculate the maximum force that can be applied on a wire of diameter 1.2 millimeters from this metal. So pause the video now and unpause the video and you'll want to go through your answer. Right, so you've got to know the definition of ultimate tensile stress. It's the maximum stress, or the maximum force, that can be applied to a material before it breaks. So I'll go with the maximum stress there. Now, describe the properties of cast iron from the graph below. Well, we can see that it doesn't have any inelastic deformation, so therefore it must be a brittle material. That's the definition of a brittle material. Only elastic deformation and very little inelastic deformation. Now, from the information given, we know that Young modulus is stress over strain. So stress is force over area. Pop in all the values. Remember, the area is pi r squared because it's a circular cross section. Now we'll go convert our diameter into radius by doing 0.20 divided by 2. We then turn it into meters by times by 10 to the minus 3. So we get out our stress. Our strain is extension over length. Extension means the difference in the length from the original divided by that original to get 0.0125. The Young modulus is stress over strain, so we get 1.6 times 10 to the 10 pascals. In this next one, we know the ultimate tensile stress is tensile strength is going to be the maximum stress, so therefore it's force over area, so therefore the force is the ultimate tensile strength times by the area. That'll give us the maximum force possible, so therefore it's 220 times 10 to the 6 megapascals into pascals times by pi r squared, so converting a diameter into a radius by dividing by 2 and millimeters into meters by times and by 10 to the minus 3, so we get 250 newtons. The next question says, for each of the materials whose stress strain graph are shown below, deduce the values of the Young modulus and their breaking stress. So pause the video now, then unpause the video and you'll want to go through your answer. Right, so in a stress strain graph, like we said before, the Young modulus is going to be the gradient of the straight line section. So it's going to be 50 gigapascals for A, and then the breaking stress is the biggest value of stress found on the graph, so the highest value for that line on the y-axis, which is 150 megapascals for A. For B, it's 100 gigapascals for the Young modulus, and the breaking stress is 130 megapascals. Now again, it's important it can only be used for the straight line section, and then for material C, once again, it's the gradient for the Young modulus, which is 25 gigapascals, and then the breaking stress is the highest value on the y-axis, which is 100 megapascals. The next question says, a steel girder is tested to find the tensile strain of a girder when a load is added. The original length of the girder is 5.00 meters. During the test, the length of the girder is remeasured. The new length of the girder is 5.04 meters. Calculate the tensile strain of the girder. Explain why tensile strain has no unit. Engineers need to inspect the metal girders of motorway bridges for signs of metal fatigue. One of the causes of metal fatigue is the large number of heavy lorries that drive over the bridge each day. Describe how heavy lorries can cause metal fatigue when driving over metal girders, and then the metal girders are made from steel. Steel is a malleable material. Explain the meaning of malleable in the term of atomic structure. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that strain is going to be extension over original length. So you find your extension by minusing the new length by the original length. We then find strain by dividing that by the original length, so it's 0.008. Now it has no unit because it's a ratio of two distances. So when you divide those two distances, if you're using the same unit, it will cancel through. Now in the next question, the lorries will deform, they'll place stress on the girder each time they cross the bridge. The heavier the weight, the greater the pressure of the lorry, the more it will deform. Now the total effect of this deformation will increase with time until failure, until it fails, so then it actually will just break. Now malleable in this context means that the atoms are in layers, or they're in a lattice, so that the atoms will slide over each other when the force is applied, so they can change shape. The next question says, figure 7.18 shows a force extension graph for a metal wire of length 2.0 meters and cross-sectional area 1.5 times 10 to the minus 7 meters squared. Calculate the Young modulus. Then determine the energy stored in the wire when the extension is 0.8 millimeters, and then calculate the work done in stretching the wire between 0.4 millimeters and 0.80 millimeters. So pause the video now and unpause the video when you want to go through your answer. Right, in this first one, you've got to remember that you can work out the Young modulus by, firstly, working out the stress and the strain, because you've got a force extension graph. So the stress is the force over the area. Now we know the area from the question, so you can work out the force by taking the maximum value, which you can see is 10, and working out the stress that way. We take the maximum value for all of them, and we can then use the Young's modulus because we kept it consistent. You could do a middle value as long as you kept them as consistent when you were working out values from the graph. Now the strain is extension over original length. We've got the original length from the question, 2 meters. So again, we go to the maximum value for the extension and we get 0.8 millimeters. So therefore converted into meters by times 10 to the minus 3, and we get our strain out. Then the Young modulus is stress over strain. So we then get 1.7 times 10 to the 11 pascals. Now the energy stored in the wire is going to be a half times by force times by extension. So when it's at 0.8 millimeters, you've got your extension there, but you convert it into meters, and then you go into the graph and find what the value for the force is at 0.8 millimeters, which is 10 newtons. It's also the area under the graph, so it's 4 times 10 to the minus 3 joules. Now we also know that work done is force times by extension. So we've got our force, that we know it's going to be 7.5 newtons between 0.4 millimeters and 0.8 millimeters. That's what our value is going to be. So therefore we can then multiply it by the extension. So therefore we get 3 times 10 to the minus 3 joules. The next question says, figure 7.19 shows the stress strain curves for 3 different materials, P, Q and R. State and explain which material has the greatest Young modulus. Then describe an experiment to determine the Young modulus for a material in the form of a wire. Include a diagram and explain how you'd make the necessary measurements. State how you'd use your measurements to calculate the Young modulus. So pause the video now, then unpause the video when you want to go through your answer. Right, again you can see that the Young modulus is the gradient. So P has the largest Young modulus because it has the steepest gradient of all of the different materials. Now You need to have a diagram showing a wire and then weights being used to stretch the wire. You'd have to think of a method of viewing an extension, so you could have like a travelling microscope, you could have a marker on the wire, you then use a series of weights to stretch that wire and then note down the extension. You would measure the diameter of the wire with a screw gauge micrometer. You'd measure the initial length of the wire with a ruler. You'd then graph the force against extension, and then the Young modulus is going to be equal to FL over AX. Or you could do a stress strain graph and then have just the gradient of the line being the Young modulus. The next question says, show that the Young modulus of a material can be calculated using the equation E equals FL over AX, where F is the force applied, L is the original length of the wire, X is the extension of the wire, and A is the cross-sectional area of the wire. Then use the equation to determine E, given that the diameter of this wire is 0.84 millimeters, the original length of the wire is 2.500 meters, the force applied is 300 newtons, and the extension is 1.4 centimeters. And then state one significant assumption made in this previous calculation. So pause the video now, then unpause the video and you want to go through your answer. Right, in this first one we know that the Young modulus is stress over strain. So we know that stress is force over area and strain is extension over original length. So you can then pop them all through and you get FL over AX. Pop in all the values for the next question. Remember, we'll convert our millimeters into meters. Now again, it's pi r squared, so you're going to half your diameter so to get into radius. You're going to have to convert your extension into meters as well to work out, so you can then work out in the values in the graph. So you can work it all through and you get 9.7 times 10 to the 10 pascals. Now, you've got to be aware the assumption that we make is that the elastic limit is not exceeded, because at that point the stress is directly proportional to the strain, so it's not exceeded. The next question says, a hollow brass cylinder with closed ends is floating on the surface of water. The cylinder has a length of 4.0 centimeters and an external diameter of 2.1 centimeters as shown. 63% of the volume of the cylinder is submerged. The cylinder contains negligible weight of air. Explain why the brass cylinder floats. Then the density of water is 1.0 times 10 to the 3 kilograms per meter cubed. Show that the mass of the cylinder is about 9 times 10 to the minus 3 kilograms. Then deduce whether an identical hollow cylinder made of gold would also float. Assume that the volume of the gold is the same as the volume of the brass. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, there's two reasons why an object would float. It's that the density of the object is less than the density of water, and that the weight of the water displaced by the cylinder is equal to the weight of the cylinder itself. Now, how can you show the mass is about 9 times 10 to the minus 3? Well, you work out the volume of the cylinder, which is pi r squared times by h. So you can work it all through, and we're going to convert our centimeters into meters. Now, we know that the volume submerged will be 63% of the volume of the cylinder, so it's 0.63 times our value. So therefore, we get 8.76 times 10 to the minus 6 meters cubed. The mass of the cylinder has to be the mass of the water displaced, so it's 1,000 kilogram per meter cubed times by 8.76 times 10 to the minus 6, so it's 8.76 times 10 to the minus 3 kilograms. In the next one, we know the volume of the gold equals the volume of the brass. So we know it's 8.73 times by 10 to the minus 3 divided by 8.7 times 10 to the minus 3. So 10 to the 3, sorry. So therefore it's 1.00 times 10 to the minus 6 meters cubed. The mass of the gold is therefore this volume times by 19.3, the percentage of it, 19.3 times 10 to the 3, which is 0.0193 kilograms. Now you can then say the volume of water required is that value divided by its density. So we get 1.93 times 10 to the minus 5 meters cubed, and this value is greater than the volume that would be displaced by this object, so therefore it would sink. The next question says, a Galilean thermometer consists of a closed glass cylinder containing a liquid. In the liquid there are several identical sealed glass bulbs as shown. Attached to each bulb is a metal disc labelled with the temperature. Each disc has a different mass. As the temperature increases, the density of the liquid decreases. This can cause the bulbs to move within the liquid. Explain why a particular bulb will float up until the temperature of the liquid exceeds a certain value. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one we know that the upthrust on a bulb is equal to the weight of the liquid displaced. Now, when the upthrust equals or exceeds the weight of the bulb will float. Now the weight of this bulb or the disc is constant because it's always in the water. Now as the temperature increases, the weight of the displaced liquid will decrease because it means that the upthrust on the bulb will decrease, because that will happen until the weight of the bulb exceeds the upthrust. Therefore there'll be a resultant force acting on the object, okay, and therefore it will mean that there's a resultant force downwards, and that will cause the bulb to sink. The next question says, the photograph shows a toy pinball machine. The launcher is pulled back, compressing a spring. The spring obeys Hooke's law. When the launcher is released, the spring returns to its original length and a small ball is launched horizontally into the machine. When the launcher is pulled back, the spring is compressed by 5.0 centimeters. When the spring is released, the ball is launched at a speed of 8.0 centimeters per second. Now, show that the kinetic energy of the ball just after launching is 4 times 10 to the minus 5 joules. The mass of the ball is 12 grams. Then determine the force on the ball when the spring is released. Then determine the stiffness of the spring. So pause the video now, then unpause the video when you want to go through your answers. Right, in this first one, we know that kinetic energy is equal to a half mv squared. Now you're going to convert your grams into kilograms by times by 10 to the minus 3, and then remember to square the value of the speed, but it's going to be in meters per second. So again, it's 8 times 10 to the minus 2, so we get 3.84 times 10 to the minus 5 joules. We know that the force on the ball. Well, how can we work it through? We know that the kinetic energy will equal the elastic potential energy, but that also equals a half fx squared, because that's the equation for elastic potential energy. So therefore, F is equal to 3.84 times 10 to the minus 5 over 0.025, and then we get 1.54 times 10 to the minus 3 newtons. Now, how do we work out the stiffness or spring constant of the spring? Well, F equals K times by extension. So therefore K is going to be equal to F over the extension. We've got the force from the previous question. We know the extension from previous information because it's just the compression. So therefore it's 0.031 newtons per meter. The next question says, figure 7.21 shows the force extension graph for a spring. State what is represented by the gradient of the graph, then the area under the graph. The spring has a spring constant of 80 newtons per meter. The spring is compressed by 0.060 meters and placed between two trolleys that run on a friction-free horizontal track. Each trolley has a mass of 0.40 kilograms. When the spring is released, the trolleys fly apart with equal speeds but in opposite directions. Firstly, how much energy is stored in the spring when it's compressed by 0.060 meters? Explain why the two trolleys must fly apart with equal speeds, and then calculate the speed of each trolley. So pause the video now, then unpause the video when you want to go through your answer. Right, you should know that for a force extension graph, the gradient is y over x, so that is going to be the force over the extension, which is the spring constant. The area is linked into the work done, so therefore it's the energy stored in the spring. So therefore, how much energy is stored in the spring here? We know energy stored is going to be elastic potential energy, which is equal to a half kx squared. We've got our value for k and we've got our value for x, but again, we've got to square it, remember, so therefore it's 0.14 joules. Now the two trolleys fly apart with equal speeds because of the conservation of momentum. The momentum of each trolley must be equal but opposite, because we know that the total momentum before is 0, so the total momentum after is 0, so it cancels through by one being positive and one being an equal magnitude in the opposite direction, which is negative. So therefore, if they have equal masses and the momentums must equal, well, their velocities must equal as well. Now the speed of the trolley, therefore we know, is going to be 2 times by half mv squared, because we know that we've got two trolleys each with the same amount of kinetic energy. So therefore we know that it's going to be in total 0.144 joules, because the elastic potential energy is turned into the kinetic energy into both of the trolleys, but there's two of them. So therefore V is going to work it through 0.60 meters per second. The next question says, this question is about the behaviour of materials under tension. A student sets up an experiment to investigate the force extension characteristics of a rubber band and obtains the data as shown. Describe the experimental technique that the student could use to gather reliable data, including your answer with how experimental uncertainties and risks can be minimised. Suggest what the greatest source of uncertainty in the experiment is. Then describe the relationship shown by the graph in figure 4.1 and explain how this relates to the behaviour of the band under tension and its microscopic structure. You may use diagrams in your answer. So pause the video now, then unpause the video and you want to go through your answer. Right, so for this particular investigation, you would suspend a rubber band from a clamp stand and then add masses and then measure the extension with a ruler for different loads. Now the source of extension is the measurement of the extension of the rubber band. Okay, so aligning it so that there's going to actually be zero extension when there's no object placed upon it, where there's no mass placed upon it. So you can minimise this by taking repeats and calculating an average. You can have a set square against a table to ensure the rule is perpendicular or use a plumb line, or you could use a fiducial marker to help eliminate parallax error. Now the risk in this experiment is you should have safety glasses on, make sure you don't exceed the breaking force of the band so that it snaps, keep your body away from the drop zone in case it does snap, or make sure that the clamp is weighed down, okay, so therefore it doesn't topple over. Now in this next question, how could they link together? Well, you've got to know for the data that the extension increases as the force increases with a non-linear relationship. So therefore, as the gradient relates to the stiffness of the material, it starts off fairly stiff or has a large force for a small extension, but over time the stiffness reduces and you get a larger extension for a smaller force before the stiffness increases again, so therefore there's more force for a smaller extension. Now rubber is a polymer. Now polymer is identified as like a long chain molecule. Now in the polymers in rubber are arranged randomly, so therefore you can also have cross links which can stiffen it, which you can see on a bit of a diagram. And then finally the polymer chains are initially tangled up. As a force is then applied to untangle the chains and break those sulfur cross links, that requires a high force for a small extension. But once you've then done that and untangled the chain, you're simply straightening out that chain, so you get a greater extension for the same force, and they can also slide over each other. Now in the final section, you're actually stretching out the carbon-carbon bonds in your polymer as well, so you're getting that extension taking place. The next question says the diameter of a wire is measured with a screw gauge micrometer as shown below. The circumference of the rotating thimble is divided into 50 equal steps, and for each full rotation of the thimble it moves a further 0.5 millimeters along the shaft. So give the resolution of a micrometer with the correct unit. Suggest how the student could use multiple measurements to find the uncertainty of the diameter of a wire. Then the student measures the diameter of another wire to be 0.35 plus or minus 0.02 millimeters. Calculate the cross-sectional area of the wire along with absolute uncertainty. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a fact that you've got to know that a micrometer has a resolution of 0.01 millimeters. Now, when you're using that to work out the diameter of a wire, yes, you've got to take multiple measurements, but you've got to take them in different places or different planes of that particular wire. Now, you can then, once you've done that, you can then work out the uncertainty because it's going to be half of the range of the values that you've been given. Now, in the last one, you're going to calculate the cross-sectional area. So what you do is say area is pi d squared over 4 because it acts as a circle, so therefore it's 9.6 times 10 to the minus 8 meters squared. Now the uncertainty is therefore going to be 0.02 over 0.35 as the absolute over the value, which is 5.7%, but that's the uncertainty in the diameter. Now the radius is, sorry, the area is pi d squared over 4, so because it's d squared, you've got to double the percentage uncertainty in the diameter, so it's 11.4%. So you find 11.4% of 9.6 times 10 to the minus 8, and you can work it through that way. The next question says, a student applied a force F to a rubber band. The student measured the corresponding extension change in X as F was increased and then decreased. The graph shows how the extension varied as the force was increased and then decreased. Firstly, state how the graph shows that the rubber band deformed elastically. Then the work done on the rubber band as the force increased is greater than the work done by the rubber band as the force was decreased. There's a difference in these values because heating occurred. Determine the energy that caused heating as F was increased and then decreased back to 0. So pause the video now and then unpause the video when you want to go through your answer. Right, you've got to remember that the definition of elastic is that it's an object that returns to its original length and shape when the force to form when it is removed. So when the force was removed, the rubber band returned to its original length because it goes back to having an extension of 0. So the decrease in force line returns to the origin. Now, next question, we know that the elastic potential energy is the area under a force extension graph. Now, if we look at 1 centimeter squared on the graph, it's going to be about 0.5 newtons times by 0.5 0.05 meters, so it's about 0.025 joules. Now if you measure it quickly through by doing some counting of squares, you'll see that the area between the two lines, the increase in force line and the decrease in force line, and the area enclosed in that is the energy lost due to hysteresis, is going to be about 19 centimeters squared. So you do 19 centimeters squared times by 0.025, so you get 0.0475 joules. The next question says, in an experiment to measure the Young modulus of glass, a student pulls out a glass rod to form a fibre 0.800 metres in length. Using a travelling microscope, she estimates its diameter to be 0.40 millimetres. Unfortunately, it proves impossible to obtain a series of readings for load and extension. The fibre snaps when a load of 1.00 newtons is hung on the end. The student judges that the fibre extended by no more than 1 millimetre before it snapped. Use these values to obtain an estimate for the Young modulus of the glass used. Explain how the actual or accepted value for the Young modulus might differ from this estimate. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know that stress is equal to force over cross-sectional area. So in this case, we know it's going to be 4F over pi d squared, because we know that the area is pi d squared over 4, so we can rearrange it like that. We pop it all in there and we get 8 times 10 to the 6 pascals. Remember, we'll convert now 0.40 millimeters into meters. Now our strain is extension over the original length, so therefore we're going to have to convert 1 millimeter into meters there, so we can have the same unit. So it's 0.001 over 0.800, so it's 1.25 times 10 to the minus 3. Now we do the Young modulus, the stress over the strain, so therefore we've got the stress, we've got the strain, so it's 6.4 times 10 to the 9 pascals. The next question says, state the meaning of tensile stress and tensile strain. Then a vertical steel wire of length 1.6 meters and cross-sectional area 1.3 times 10 to the minus 6 meters squared carries a weight of 60 newtons. The Young modulus for steel is 2.1 times 10 to the 11 pascals. Calculate the stress in the wire, the strain in the wire, and the extension produced in the wire by the weight. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know that the tensile stress is the ratio of the force to the cross-sectional area of the wire. Stress is force over area, while tensile strain is the ratio of the extension to the initial length. It's extension over original length. So stress is force over area, so you can pop in all those values and you get 4.6 times 10 to 7 pascals. Strain is going to be stress over the extension, so the Young modulus, my apologies. So strain is stress over the Young modulus, so we pop those values in and we get the answer to be 2.2 times 10 to the minus 4, no units, it's a ratio. Now the extension, we can work it through because we know strain is extension over original length, so extension is strain times by original length, so therefore it's 2.2 times 10 to the minus 4 times by 1.6, so therefore it's 3.5 times 10 to the minus 4 meters. The next question says, to allow for expansion in the summer when temperatures rise, a steel railway line laid in cold weather is pre-stressed by applying a force of 2.6 times 10 to the 5 newtons to the rail of cross-sectional area 5.0 times 10 to the minus 3 meters squared. If the railway line is not pre-stressed, then a strain of 1.4 times 10 to the minus 5 is caused by each degree Celsius rise in temperature. The Young modulus of the steel is 2.1 times 10 to the 11 pascals. State and explain whether the force applied to the rail when it is laid should be tensile or compressive. Then calculate the strain produced when the rail is laid, and then calculate the temperature rise when the rail becomes unstressed. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that it should be a tensile force because the railway expands on heating and therefore that would reduce the stress, so you want it to be a tensile force applied to it. Now, the next one, we know stress is force over area, so we've got the force from the information in the question, we've got the cross-sectional area, so you can work out the stress. We then know strain is stress over the Young modulus, which we do know from the information given, so it's 2.5 times 10 to the minus 4 meters. Now we know the temperature rise, well we know that if a strain of 1.4 times 10 to the minus 5 is caused by each degree rise in temperature. Now we know that the overall strain from the previous question is 2.48 times 10 to the minus 4, so do 1 divided by the other and we get 18 degrees Celsius. The next question says, figure 7.20 shows the stress strain graph for a metal wire. The wire has a diameter of 0.84 millimeters and a natural length of 3.4 meters. Use the graph to determine the Young modulus of the wire, the extension of the wire when the stress is 0.6 gigapascals, the force which causes the wire to break assuming the cross-sectional area of the wire remains constant, and the energy stored when the wire has a stress of 0.6 gigapascals. So pause the video now, then unpause the video when you want to go through your answer. Right, now we know that the Young modulus is the gradient of the straight line section of the graph. So you can work that through and we get 1.5 times 10 to the 11 pascals. In this one, you've got to use the graph and read it through. So you can see that when the stress is 0.6 gigapascals, well then the strain is 4.0 times 10 to the minus 3. We know that strain is the extension over the length, so therefore extension is the length times by the strain. We can see what the length is from the question, is 3.5 meters, so we get 1.4 times 10 to the minus 2 meters. Now how can you work through the force? Well, the breaking stress is the breaking force divided by the area, so the breaking force is going to be the stress times by the cross-sectional area. Now remember, we're given diameter in millimeters, so we half it to get the radius. We times by 10 to the minus 3 to get it into meters squared, so into meters, my apologies. Then we can say pi r squared to work out the cross-sectional area, and we get out 840 newtons. Now the energy stored is actually going to be the area under the graph, so what you can do is you can actually say, well, at 0.6 gigapascals, we know that what the force is going to be because we've got our value for stress and we know the value for area. So we can say it's 333 newtons. The energy stored is the area underneath, which is a half Fx. So therefore it's going to be a half times by 333 times by 1.4 times 10 to the minus 2, which is 2.3 joules. The next question says, a gymnast bounces on a trampoline. For part of each bounce, the gymnast is in contact with the trampoline. For the rest of each bounce, the gymnast is in the air. The trampoline gives the gymnast a maximum upwards acceleration of 14.2 meters per second squared. Calculate the maximum upwards force of the trampoline on the gymnast. The mass of the gymnast is 58 kilograms. The trampoline is made of a sheet of material attached to a frame by springs. The vertical components of the tension in the springs provide the upward force on the gymnast. The vertical components of the tension in one spring is 68 newtons when the spring makes an angle to the horizontal of 14 degrees as shown below, so that the tension of the spring is about 300 newtons, and then the extension of the spring was 4.6 times 10 to the minus 2 meters. Calculate the stiffness of the spring. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we know that the overall force is going to be P minus W. So therefore, the resultant force is MA, then it equals to the T there, the tension, then minus mg. So you pop it all through, you work it all out, and then you can pop out the value to be P equals minus 58 kilograms times by 9.81, so therefore works it all through and you get 1.39 times 10 to the 3 newtons. We can then show that actually that we know that T sine 14 is equal to 68 because we've got our vertical component, T sine 14 is equal to 68 as told in the questions. Therefore T, when you work it through, is 281 newtons, and then the extension, well, we can say, right, well, F is equal to Kx, so therefore we can work out K by doing F over X, and therefore we get 6.11 times 10 to the 3 newtons per meter. The next question says, an empty lift is positioned at the first floor of a building. It is suspended by 6 identical steel cables of length 50 meters. Calculate the extension of each each lift cable. The cross-sectional area of the cable is 3.1 times 10 to the minus 4 meters squared. The Young modulus of the steel is 200 gigapascals, and the weight of the lift is 12 kilonewtons. Then 10 people enter the lift. It says that after 5 seconds the lift starts to move upwards and stops at the top floor of the building. At that point, the graph shows the total tension force in the cables during this time. Now, calculate the total mass of the people in the lift. Now, the weight of the lift is 12 kilonewtons. Then explain the motion of the lift between 5 seconds and 29 seconds. Then when the lift is empty, a technician removes one of the cables for maintenance. Assess how removing one cable would affect the extension of the remaining cables. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we can say that stress is force over area. We've got our force, we've got our area. So it's 6.45 times 10 to 6 pascals. We know that the Young modulus is stress over strain. So therefore, we can say that the strain is going to be working through to be the stress divided by the Young modulus, which we've got the answer for. So it's 3.23 times 10 to the minus 5. Extension is that strain times by the original length. So it's 1.61 times 10 to the minus 3 meters. We know the total weight of the people. cable is going to be 19 kilonewtons minus 12 kilonewtons, because it's going to be the resultant force downwards. We also know weight equals mg, so therefore m is going to be the weight, so going to be weight over g, so therefore 7 times 10 to the 3, which is 7 kilonewtons, divided by 9.81, which is 714 kilograms. Now between 5 seconds and 29 seconds, well, from 5 seconds to 6.5 seconds the lift accelerates upwards. From the 6.5 seconds to 27.5 seconds it'll then travel upwards at a constant speed. Then from 27.5 seconds to 29 seconds it'll accelerate to rest. Now again, this is because from 5 to 6.5 seconds there's a resultant force upwards. As you can see from the graph, from 6.5 seconds to 27.5 seconds a resultant force is 0, and then from 27.5 seconds to 29 seconds there's a resultant force downwards. Now in this last question, if you remove one cable, well then the tension in each of the remaining cables would increase, but the total force remains the same. But the total cable area has decreased, so therefore the stress in each cable would have to increase when you work out stresses force over area. So because the area has gone down but the force remains the same, the stress has gone up. So with an increased stress, that gives you a greater strain, because strain is caused by stress, so therefore the extension of each cable will be a greater value. The next question says, a solid spherical component has a diameter of 0.06 meters and a mass of 0.35 kilograms. The component is made from an unknown material. Calculate the volume of the spherical component and then calculate the density of the unknown material. So pause the video now, then unpause the video and you want to go through your answer. Right, so what you would do is you would work out the radius by saying the radius is the diameter divided by 2. So therefore you could say the volume is 4 over 3 pi r cubed, and work it through to be 111.1 times 10 to the minus 6 meters cubed. Density is mass over volume. It's the mass of the value, 0.35, divided by the value we just calculated to get 3094.6 kilograms per meter cubed. The next question says, a student carried out an investigation on the spring to test this information. She applied a range of forces from 0 newtons to 5 newtons to the spring. She measured the length of the spring and recorded the extension for each force. She plotted out a graph of force against extension, determined the stiffness of the spring, and discussed the extent to which the student's results are consistent with the information given by the manufacturer. So pause the video now, then unpause the video and you'll want to go through your answer. Right, in this first one, it's got to be the stiffness is the gradient of a force extension graph. So therefore, it's the gradient of the line, which when you draw it in is 20 newtons per meter. Now we can say here that the spring constant is going to be about between 19.95 to 22.0 newtons per meter. We know the force is the spring constant times the extension, so therefore it's 8 newtons. Now we can then say that the elastic potential energy is a half times by the force times by the extension, so it works out to be 1.6 joules. Now we also know we've got a straight line graph going through the origin, which is again consistent to Hooke's law as stated. Now again, we've got to understand that the maximum extended length, which is 400 millimeters, is not covered by the student's results because they only go up to 300 millimeters. The calculated energy value is compared to 1.6 joules, and we give a conclusion whether it's close or not. We can then work out the range in the manufacturer's uncertainty, see if it's right. We could calculate the percentage difference between the value we have and their value, and then we could calculate that. But now it's trying to say, well, if it's in 5%, it would be appropriate. The next question says, a type of exercise device is used to provide resistive forces when a person applies compressive forces to its handles. The stiff spring inside the device compresses as shown in the figure below. The force exerted by the spring over a range of compressions was measured. The results are plotted on the grid below. State Hooke's law. State what two features of the graph confirm the spring obeys Hooke's law over the range of tested values used. Use the graph to calculate the spring constant, stating an appropriate unit. So pause the video now, then unpause the video and you'll want to go through your answer. Right, learn what Hooke's law is. It's the deforming force on the material is directly proportional to the extension of the material it causes up to the elastic limit. Now the two features of the graph that showed obeys Hooke's law are it's a straight line and it's going through the origin because it's shown direct proportionality. Now the graph will give you the spring constant by working out the gradient of the line, which is going to be about 1290 newtons per meter. The next question says, a manufacturer of a spring tests the properties of a spring by measuring the load applied each time the extension is increased. The graph of the load against extension is shown below. State Hooke's law, then calculate the spring constant for the spring and state an appropriate unit. Use the graph to find the work done on extending the spring up to point B. Beyond point A, the spring undergoes plastic deformation. Explain the term elastic deformation. So pause the video now, then unpause the video when you want to go through your answer. Right, so Hooke's law, like I said, is the force is directly proportional to the extension up to the limit of proportionality. The spring constant is the gradient of the force extension graph, so it's about 1,100 newtons per meter. The work done is the area under the graph, so when you work it through, you're getting about 1.1 joules. And plastic or inelastic deformation is when you have a permanent deformation when the deformant force acting upon it is removed. It's the opposite of elastic. The next question says, a spring has a spring constant of 240 newtons per meter with a tolerance of plus or minus 5% supplied by your manufacturer. The maximum energy that the spring can store safely is 90 joules. A laboratory technician uses the spring in an experimental arrangement and measures the extension with a ruler that has a resolution of plus or minus 1 centimeter. The extension is recorded as 85 centimeters. Determine the energy stored in the spring along with its absolute uncertainty. Explain why it may not be safe. So pause the video now, then unpause the video when you want to go through your answer. Right, well we know that the energy stored is elastic potential energy, so we can say it's a half kx squared. Now we've got the extension and we've got the spring constant, so it works through to be 86.7 joules. Now we can also say we can work out what our uncertainty is, because we know it's going to be plus or minus, well, it's going to be 0.05, which is that 5%, plus 2 times by 1 over 85. Now we're doing it like that way because we know it's been squared, so therefore we're multiplying the percentage uncertainty by 2. So ultimately we get 0.07 or 7% when it works through. So therefore we're going to multiply that 86.7 by that 7% and we get 6 joules out. So therefore the work done is 87 plus or minus 6 joules, which could be bigger than 90, which is the safe limit, so it could be 93 in theory, so it is unsafe. The next question says, a student investigated how the extension of a rubber cord varied with the force used to extend it. She measured the extension for successive increases of the force and then for the successive decreases. The diagram below shows the graph of her results. Give a reason that the rubber cord does not obey Hooke's law. Give a reason why the graph shows the rubber cord does not exhibit plastic behaviour. What physical quantity is represented on the area shaded between the load and curve and the extension axis. And then describe with the aid of a diagram the procedure and measurements you would use to carry out this investigation. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, it doesn't obey Hooke's law because the line is on a straight line. Now, it doesn't exhibit plastic behaviour because it returns back to the origin. It doesn't have any change in extension once the deformant force has been removed. The physical quantity is the work done or the energy stored on the rubber cord. And in this last question, you'd have a rubber cord fixed at one end with a weight on the other end. You'd then apply a variable force by using different masses. You would then measure the cord and then work out the force applied and the extension of the cord. Do it for different values of force or weight, and then you can work out your different extensions and plot your graph. The next question says, a stress strain graph for a ductile metal is shown. Identify and describe the key features shown by the graph. References to atoms, ions and molecules is not required. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know that initially the ductile material obeys Hooke's law and undergoes elastic stretching, both of which are shown by this straight line portion. The limit of the linear portion is called the limit of proportionality, and the gradient of the straight line is the Young modulus. Beyond the limit of proportionality is the elastic limit. Beyond this point, the material will not return to its original shape when the deformant force on it is removed. The yield point is the point at which the material undergoes a large increase for strain, or for little to no increase in stress. The maximum stress is the breaking stress, or the ultimate tensile stress. Now the material will go elastic, then it will go inelastic deformation, and then will reach the breaking force. The curve bends downwards beyond the maximum stress because it exhibits necking, so it will actually narrow before it snaps. The next question says, a steel object is held by an electromagnet. The magnetic force prevents the steel object falling. State 2 reasons why the weight of the object and the force of the electromagnet are not a Newton's third law pair. Then the electromagnet is suspended from a support by a steel cable as shown. When the object is suspended, the strain in the cable is 3.0 times 10 to the minus 4. Calculate the Young modulus of steel in the cable. The cross-sectional area of the cable is 5.1 times 10 to the minus 4 meters squared. The unstretched length of the cable is 3.8 meters, and the stiffness of the cable is 2.8 times 10 to 7 newtons per meter. The force extension graph for a steel cable is shown below. When the electromagnet is switched off, the steel cable falls. A student states that the change in the elastic strain energy stored in the cable will be transferred to the gravitational potential energy of the electromagnet. Discuss the student's statement, and you can add to the force extension graph as part of your discussion. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, there can't be a third law pair because they act on the same object, not different objects, and they're not the same type of force, both which are needed for a Newton's third law pair. In this next question, we know extension is equal to the Young modulus times by the initial length, so it's 1.14 times 10 to the minus 3 meters. Force is then the spring constant times the extension. We've got the extension now, so we multiply it by our spring constant, and we get 3.19 times 10 to the 4 newtons. We then know stress is the force over the area. We've just worked out the force. We know the area from the information given, so we get 6.26 times 10 to the 7 pascals, and then we know that the Young modulus is stress over strain. Divide one by the other, and we get 2.0 times 10 to the 11 pascals. Now in this last graph, we know the area under the graph is the elastic strain energy. Now once you've still released that particular steel object, the weight of the electromagnet is still exerted on the cable. So any change in elastic strain energy will equal the area under the graph between the total weight of the electromagnet and the steel object and just the weight of the electromagnet itself. So there'll be a difference in the areas due to that. Now any change in the gravitational potential energy of the electromagnet will be equal to the weight of the electromagnet times by that change in extension that the cable would experience. So therefore it's important to understand that therefore the change in elastic strain energy stored will be greater than the gravitational potential energy of that electromagnet due to that reason. So that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you for listening to this revision session on materials, and have a lovely day.